Hello everybody, my name is Caitlin Riley and I'm going to be talking to you about Napoleon's theorem. So first, quick recall how to rewrite an angle or a rotation with an angle that's between 0 and 360. So if we were going to start on the x-axis and rotate negative 120 degrees, that means we would be going this direction, and this would be negative 90, this is negative 180, so we end up somewhere in here with degrees from the x-axis. That's our 60 right there. So to write that with an angle in the positive direction, that means we would be starting from the same spot and going counterclockwise. We'd be going all the way to 180 plus that extra 60. So that would be a rotation of 240 degrees. And that's a piece of information that we're going to be using a little bit later on in our proof. So just to introduce Napoleon, he was a French conqueror and emperor, and he was accredited with the theorem that states if we're given a triangle ABC, and we form equilateral triangles on each side, if we connect its centers, that triangle is also equilateral. So I drew the diagram with maybe a little less lines and color-coded, hopefully to help you see it a little bit better. So right here, we have our original triangle ABC in the middle. We have our pink, purple, and blue equilateral triangle. And then here are my centers in black. If we connect the centers, this triangle is always equilateral. That's what Napoleon discovered. Connecting those centers forms an equilateral triangle. So we're going to check out first. We're going to simplify this diagram a little bit more even. We're just going to pretty much focus on the pink and the purple triangle. And we're going to use properties of an equilateral triangle to help us show that it's equilateral. So if we remember that an equilateral triangle has 60 degrees for each angle, the center to each vertex is congruent. Same is going to be for this equilateral triangle over here. P is my center, which means these pieces are congruent. The pieces that go from the center to the vertex is also an angle bisector, which means we're going to get 30 degrees in here. Same will be true over here. Which leaves this up here as 120 degrees. So here we have an isosceles triangle with 120 degrees up here. So you can start to see that we have A rotated about Q, lands us here, and this point rotated about B, lands us over at C. So we're going to look at the composition of this double rotation about two different points, about Q and about P. And we're going to try to write it as a single rotation. So the way we do that is we actually first look at it as a double reflection. So let me just get my ruler here so I'm nice and straight. So we were going to rotate about point Q. That means that from the any pair of lines corollary, it's equal to a double reflection that has to go through, I'm a little off, that has to go through point Q. The angle between those two lines, the directed angle between those two lines, is half of our angle of rotation, which means that's where our 60 degrees is going to come into right here. And we can label these lines K and I, for example. And we're going to do the same thing with our second reflection, our second rotation about point P. From the any pair of lines corollary, it's equal to a double reflection. Try not to get tongue-tied here. As long as those two lines go through our point of rotation. Oops, it's a little off. Let's try that again. So we'll call this line L and this line J. Goes through our point P, and it has the directed angle of half the angle of rotation, which is again 60 degrees. So we're starting to see our equilateral triangle come to light here a little bit. So since we're trying to write it as a single rotation, a clever choice would be to make line I equal to line L. So if we kind of redraw, and I'll just redraw my centers here, Q and P. And I'm going to draw that line, we'll call it I, and it has to go through both points. That looks like a J. Has to go through both points. And now we have to draw our lines K and J. So you can kind of maybe visually see if we had this and we went kind of this way, our line K would be coming, let's use a ruler. This is our line K. And then our directed angle goes this way. And if you can kind of picture where J would be coming down this way, about this, with our directed angle going here, 60 and 60, half the angle of rotation. Then if we're trying to write it as a single rotation, the point, the turn center, is where those two lines, J and K, are going to intersect. We'll call it point O. And in order to get the turn angle, we have to look. So first we have to see if we're going to be getting this angle or this angle. Which one is going to work for our diagram? So let's see. If we have to go from Do we have to go from K to J or J to K? Well, it looks like we went over K first, so we are going for this angle because we have to go from K to J. That's the order of reflections, over K and then over J. So also using my angles, my rotation, my angle here, I know I'm going this way. So in order to figure out that angle, we know that this is also going to be 60 from this triangle inside here, which means that this angle is going to be 120. So our turn angle is going to be twice our angle between K and J. So this should set you up nicely for part 2 of our video. Thank you.